So back to that example that we had at the end of class last time. Was this rumor example? What page is that on? What page is the rumor example on? Go and flip over to that. Was this? Module 4, Investigation 1. Module 4, Investigation 1. 128? 128, page 128. Okay, so we're talking about the number of people who know this secret, and there's 3 ways to show this value of this number. What we call decimal notation, which is just the value, okay? So 48 people, that's called decimal notation. Product notation shows this string of numbers multiplied together. That also shows how many people have learned the rumor. And then exponential notation, okay? So we're going to focus on the product notation right here. So what number of people is this? So this 3 times 2 times 2 times 2 times 2 is talking about specifically what number of people? I mean, yes, it's 48, but what does it mean? What 48 people? What's that? Know the secret on that day. What day? On the 4th day. So how is it that product notation gives us the number of people that have learned, the total number of people who have learned the secret on the 4th day? How does that work? Why that calculation? Why that calculation to get us the number of people who know the secret on the 4th day? Tell me your name again. Sean. Starts out with 3 people. Doubles every day for 4 days. So every day that goes by, you're going to have twice as many as the previous day. So you're going to have, what, as many 2s as there are days that have gone by, multiplied together, right? Okay, so I want you to write the product notation for the number of people who have learned the secret on the 37th day. If you have a shortcut that you want to use, but it's still product notation. So is there a way you can do this without hurting your hand, right? But you still want to have the spirit of product notation. Okay? Still want to have the spirit of product notation. So give me the spirit of it. What would product notation be like to show or represent the number of people who have learned the secret on the 37th day? What would that be like? Mitchell?
3 times 2 to the 37.
That's not product notation. 3 times 2?
37 times.
37 times. So we can just write a couple here. And then we can say ... And then we can say what? 37 2s, right? 37 factors of 2. And that's product notation. Because for as many days as gone by, that's the number of times that we've doubled. That's the number of times that you've doubled. So we're getting close to probably maybe the world's population here. Or more. Okay, so does this idea make sense? So I forgot my very cool slide. So let's go back to this. It's my introduction. So we kind of jumped into it without introducing it because I didn't have the screen last time. So we're talking about exponential growth. Okay, so this thing with the rumors is about exponential growth. So which of these two functions shows exponential growth? Which of these two? The purple or the red? Purple. Both. Both of these show exponential growth. Okay, and so the point in showing you this is that there's a myth. Okay, there's a myth in the world. Okay, so Mythbusters, right? Mythbusters. Myth is that if a quantity grows exponentially, that means that it increases super fast. It just takes off. It accelerates upward. We use this in everyday language all the time. You hear people saying, it's growing exponentially. And what do they mean? Just rapidly. That's all they mean, is rapidly. Okay? But this red one here, that I've used my graphing software to graph, that's an exponential function. That's an absolutely legitimate exponential function. So this idea that exponential growth just means super rapid, accelerated growth, the way that we use it in everyday language, that's a myth. That's a myth. Okay, so which of these represent exponential growth? You know that you're on to me, right? So this is neither. This is neither. Here's the myth number two. Myth number two. If it's a curve, it's exponential growth. So now we're getting more into like thinking about mathematically representing exponential growth. And so I hear students saying all the time, they just see a curve, maybe that's based on an exponent, and so it's exponential growth. Neither of these are exponential growth. So there are many, many, many types of curves that model real-world things. But exponential growth is a very specific type of curve or type of growth. And so we want to know exactly what do we mean by exponential growth. Okay? So it doesn't just mean curved, a curved graph. Okay? There's gazillion different kinds of different kinds of growth that are modeled by curved graphs. Exponential growth is just one of them. Okay? So we want to really know it. So going back to this, we're starting to, as we talk about this product notation, we're getting to the heart of what real exponential growth is. So do you have a table like this in your book? Okay, so notice we have a couple quantities here. X is the day number, and Y is the number of people who learn the secret on day X. So if we wanted to build a function, we want to identify input and output. What is the input in this situation, or what would make a convenient input in this situation? Yeah, number of days, right? So that's our, I wrote out, said input and I wrote output because I was getting to the next question. The next question is then, where do we see the output in this table? Where's the output? Which of the remaining columns is the output? Decimal? All three. They're just different ways of saying the same number. So all three of these are the output. Okay? So we said, so what is this particular secret, the way the secret grows? In general, is it about what? What do they say? That the number of people that knows the secret does what? Doubles, right? It's just doubling. Okay? So in terms of input and output, how can we think of doubling in terms of input and output? So maybe let's write here. The blank is doubled to get the blank. Okay, so we're going to fill in the blanks. So you're going to fill in the blanks with input or output. So for instance, the input is doubled to get the output. The output is doubled to get the input, or something like that. So I want you to think about what you're looking at here, what's in terms of doubling, and fill in the blanks with either input or output in both blanks. How would you complete that statement? By filling in the blanks with either input or output in both blanks, and then talk to the person next to you. Go. Fill in the blanks. Yeah, and that's not for these quick questions. Like it's just going to be like a minute.
Yeah. Okay. Well, that's why I was
But when
asking.
when I put them to work, like when I do the attendance and give them a longer task.
Okay. Yeah.
Thanks.
Sounds good.
Okay, let's hear some thoughts about this. So, what is doubled to get what? What is doubled to get what in this? She said the output is doubled to get the input. So let's check that. So here we've got an out. Is this an output right here? It's an output 6. And so I'm going to double that, and I get 12. And is that the input? That's the input. No? The output is doubled to get the output. Any other possibilities? Yeah? The input is doubled to get the output. Let's try that. So here's the input of 2, right? And now I'm going to double that. What do I get when I double that input, Matt? 4. Is that the output? 4? So you're telling me that you double the input and it gives you the output. Doesn't work, right? It doesn't work. Do we have it? So what is it? What's getting doubled to get what? What's that? To get? She said the previous output is doubled to get the new output. Hopefully hopefully you see that. That's what's happening. You multiply it by the output to get the next output. That's what's happening here. This is key. High five. The output is doubled to get the next output. Or the previous output is doubled to get the current output, whatever you want to say. Output is doubled to get this is key. And this is what exponential growth is about. So doubling is the same as what? Mathematically, what is doubling? Multiplying by 2. So every time we're multiplying by 2 to get the next output. And we see that in the product notation because we get one more 2 in the list each time. Okay, so notice this number stays the same, this multiplier. If we double every time, then that multiplier will always be 2. Will always be 2. So we have a name for this. This is kind of what all exponential growth revolves around, is this number that stays the same, that's our multiplier on output to get the next output. And that's called the growth factor. Or, yeah, so for now, growth factor, that's fine. What is a growth factor? It's a multiplier on output to get the next output. The whole module 4 is going to come, almost all of it's going to come back to this every time. So learn it now and don't forget. So it's the multiplier on the output to get the next output. That's the growth factor. In this case, the growth factor is 2. So if you have a growth factor like 10, then what kind of growth do you get? Every time you advance the input by 1, it's going to multiply the output by 10. And so what kind of growth is that? Slow or fast? Super fast growth, right? So this is what we think of as exponential growth. But what if the growth factor was 0.01? Or I should say like 1.01. 1.01. All right? Well, if as long as it stays 1.01, then it's exponential growth because you have this constant number that you keep multiplying the output by. But you're going to get super slow growth, like the red graph I showed you, right? It's just going to gradually go up. Okay? Okay, so let's write the function. If x is so I'm going to write a function, and it's let's see, it's the secret function, so we'll call it g. I don't know, g. So okay, so before we do that, this number 98304, what's the product notation? So I want you to do product notation for the 15th day. Product notation for the 15th day. Go. So how would you represent that? Product notation for the number of people on the 15th day. So who can describe what the product notation would be? Tell me your name again. Chad. Uh-huh. 3 times 15 twos. Perfect. 3 times 15 twos multiplied together. $15 twos. Okay? So exponential growth is then, or exponential form is a way to conveniently write this. So it'd be 3 times. So the exponent here is purely a matter of convenience. It just makes this product notation easier to write. What's the main operation involved in exponential growth? What's it about? What's that? Multiplying. It's not about exponentiation. The exponent is just a convenience. It's a way of writing that 2 to the, when you see 2 to the 15th, you should be thinking what? 15 twos multiplied together. It's about repeated multiplication. That's what it is. This is just convenience to represent repeated multiplication. That's what exponential growth is about. Repeated multiplication by the growth factor. It's not about exponentiation. Again, exponent is just a convenience factor, so we don't have to write this awkward 3 times 2 and then 15 twos, right? That's real awkward. This is just a nice short way to say, take 2 and multiply it together 15 times. Okay, so then what about on the xth day? Or let's do t. Let's change it to t. So on the t'th day, that's our input. So we'd have g of t. And what would be the rule to get the number of people who have learned the secret? Is it Alexis? Can you tell me the rule then? If we go t days, so 3 times 2 times t to the t. How'd you do? And what does 2 to the t represent? When you see 2 to the t, you see 2 to the t, but you think what? Was it? T2s added, multiplied together, right? So it's about multiplication of t number of 2s. T number of 2s multiplied together. That's what you should think when you see that. What's that? T2s. So whatever the day number is, you're going to have that many 2s multiplied together because every day it doubles. So after 15 days, 15 2s multiplied together, that's 2 to the 15th. After 40 days, 40 2s multiplied together, 2 to the 40th. Okay. Questions? So let me give you an example here. I'll make this bigger. What about this? Okay, so the red is the initial instructions. I can make it still a little bigger here. Let's try 250. Okay, So initially, a certain type of cell is such that each cell splits into 4 cells every hour. Initially, there are 7 cells in a particular sample. Answer 1 through 4 to analyze and model how the number of cells in the sample changes. So you've got 4 things to do there in the blue. Okay, determine input and output quantities, define variables x and y. We're going to keep doing this all semester, practicing defining variables well. Okay? Complete the table. I want you to use product notation. See this right here? Practice product notation because this is really what it's about. So in this, when you start filling in your table, use product notation. Then number 3, explain specifically how the sample grows, what's the key operation, and define the function that models the growth. So you've got a good chunk of work to do. You can work together. Jerome can help you, and I'll take roll. Okay? Of x. Good definition of x. John?
The number of hours elapsed since the first cells split.
Number of hours elapsed since the initial number of cells. Yeah, it's good. Or I said, there's different ways to say it, but you got just as long as you have the reference point. Okay, so I said since the first observation. Okay, why? What would that be? Yeah.
I said the number of current cells.
Current number of cells. Number of cells present. Sure. Good. Okay, product notation. So that's our input and output quantities. Complete the table. Product notation. How many cells present after 0 hours? 7. Start with 7. So when we talk about, an important thing, and this is going to be the initial value. Does the initial value correspond to 1 or 0 for input? Initial value. Nope. Initial value depend on, is it when the input is 1 or the input is 0? 0. Okay, so sometimes that gets confusing. Students think that initial value corresponds to an input of 1. No, it's always input of 0. Okay? Product notation for after 1 hour. After 1 hour. Jessica? 7 times 4. What do you think? That's it. 2. Natalie? 7 times 4 times 4. After 3 hours. Let's see. Jad? 3 4s multiplied together. Okay, 20. After 20 hours. Nicholas? This Nicholas here. It'd be 4 20s? 24s, right? Yep, 24s. So the reason that we emphasize this is because then when we're always looking at exponents, this meaning gets lost. So we're really emphasizing this because when you look at it with an exponent, so what would the exponential form of that be? What would the exponential form of that be? 7 times. So all throughout this module, when you see 7 times or 4 to the 20th, you don't want to lose sight of what it means. 24s multiplied together. That's what you think when you see 4 to the 20th. Okay? After T hours. Michaela, after T hours, how would you say the product notation? 7 times 4 T times. T 4s. Okay? What's the key operation at work? Michael, what's the key operation at work? Multiplication, right? Exponent is just for convenience. So we want to write the function. Who thinks they can write the function from scratch? Who's got it? Eitan?
G of 7 equals 7 times 4 to the
What, I'm sorry, what did you call your function?
G.
G of?
G of 7 equals 7 times 4 to the x.
Did I write down what you told me? Is that right?
That's right.
So what do we want the input to be?
7.
It should be x, right? So it can be any number of hours. So I didn't tell you what to name it. So you could have named it P or C for cells, C of x. Or you could have done C of t. You could have made your input t. But this is a valid definition of this growth. Okay, so let's summarize again. Let's summarize what is exponential growth. So any questions on this example? So when you see 4 to the x, what do you think? What do you think? Joshua, is that right? Josh, what do you think when you see 4 to the x? Or what should you think?
4 multiplied by the input. However many 4 times.
How many 4? So how many 4s? Multiplied together.
Basic amount of days. Or hours, I'm sorry.
Right. So x is the number of hours. Whatever that number of hours is, it's the number of times that you're going to multiply 4 together. Because for every hour that went by, you quadrupled. So you're going to have that many 4s times 7. So 4 to the x is 4 multiplied together x times. All right? So let's summarize down there at the bottom. See that at the bottom? Exponential functions, what is it about? It's about repeated multiplication by the same value over and over again. Repeated multiplication by the same value over and over again. So exponential functions are about multiplication. They're about multiplication. All right? And what is that multiplier called? What do we call it? Growth factor. The multiplier is called the growth factor. And the growth factor, it's a multiplier on what to give what? A multiplier on what to give what? Christian, is it? Yeah. So the multiplier is, it multiplies on what to give what? Remember? It multiplies on the input to give the output. Kenneth, you agree with that? The growth factor multiplies on the input to give an output. He agrees. Eric? Okay, what do you think? Yep, that's what it is. See, look at what's happening up here in our table. What are we multiplying 4 by? The previous number of cells to get the new number of cells. Those are all outputs. That 4 keeps multiplying on the output to get the next output. Okay? So the multiplier is called the growth factor. The growth factor is a multiplier on output of the function to get the next output of the function. Because kind of what's the focus here? The focus is on the number of cells. How is that growing? So it's going to be a number of cells. It's going to grow to get a new number of cells. So it's output to output by the same multiplicative factor, which is called the growth factor. Okay, so you have in your book, I think the next section is something about page 131. So on page 131, it's about local enrollments at a school. So I'm going to change the situation. So everyone make sure you're paying attention here. Because what will happen is you go to work and then people won't catch this and you did all the wrong work. I'm going to change this. We're going to have both schools increasing in enrollment. Right now it says that school number 2 is decreasing. Just change decrease for school number 2 to increase. Okay? They both say decrease. They're both going to increase then. Change them both to increase. So school number 1 is going to increase by 3% per year. School number 2 is going to increase by 20 students per year. Did everyone get the memo? Everyone got the memo. Change both types of growth there of both schools to increasing instead of decreasing. And so what you're going to do is you're going to fill out the first half of those tables below. Work on the first half of those tables in part B, which is tracking the enrollment year by year. Okay, so fill out those tables. Just go about halfway down on each. Okay, go.
Professor,
Yeah.
So are we supposed to write the product notation for this or find out?
No, you don't do product notation. Just you can write down actual decimal notation. Yeah, don't worry about product notation. Just fill in values in the table. Just do the first 4 years for each. 4 years only. Just 4 years. Wow.
Did you mark Faisal and Fahid here?
Say it again?
Faisal and Fahid?
Yeah, huh?
Okay, they were concerned they didn't hear
Right.
you call it their name,
Yeah.
so okay. I figured you probably recognized it.
Yeah.
Okay.
Okay, so the right table should be easy, right? What's characterizing the growth there? What do you do every time to get the next enrollment? Add 20, right? It's just the change in enrollment is always 20 more than before, right? So you just keep adding 20. I'm guessing some of you did this. If you have 3% growth, you first found 3% of 1980. Anyone got that number? 59.4? And so then that was the amount of increase, 3%. So then you would do what then? Add that to 1980. So what do you get when you do that? 20, 39? 0.4, so you know, don't have 0.4 per person, so we'll just leave it 39. So watch. So just watch this quick. So really, didn't we just take 1980 times 0.03 and we added 1980? Is that right? To get that next value? So watch. If I factor out 1980, I'm left with 1 plus 0.03, which is the same as 1980 times 1.03. So really, this was about multiplying by 1.03. And you could do the same thing for all of these, because what, you're going to add the previous one plus 3% of the previous one. So what do you notice here about South High School? How is the output growing? By doing what? 3% increase is the same as multiplying by 1.03. The 1 is from the 4, and the 0.03 is the new increase. What kind of growth is that? Exponential growth. That's the growth factor, 1.03. You keep multiplying by 1.03. Multiplicative growth versus additive growth. Constant rate of change. That's constant rate of change. You keep adding by the same amount each time. Versus exponential growth, you keep multiplying by the same amount. Okay, web work for Friday and quiz. I'll post a quiz for recitation coming up.